Now it is your turn to write some code. In these labs, you will build and stress this chapter's operations and try each one yourself before you look at the solution. This is Lab 1. Your goal is to build a fixed capacity circular queue. In C, it must reject overflow and underflow instead of corrupting data. Take your time. You have about 25 minutes. The first function to write is enqueue. It adds a value to the rear of the queue. It returns 0 if the queue is full, and 1 if the value was added. The second function is dequeue. It removes a value from the front and writes it into out. It returns 0 if the queue is empty, and 1 if a value was removed. Back the queue with an array of size capacity, plus front, rear, and count. To test it, use capacity 3. In Q1, 2, and 3, all 3 succeed. Now in Q4, it is rejected because the queue is full. Dequeue once, then in Q4 again. This time it succeeds. One key hint before you start. Guard both directions before you touch any index. Enqueue must check is full first. Dequeue must check is empty first. Do the check before any pointer or index moves. Let's look at one solution. Try your own version first, then compare it with this one, line by line. Start with 2 tiny helpers. Q full is true when Q arrow count is equal to Q arrow capacity. Q empty is true when Q arrow count is equal to 0. These read cleanly and keep the guard short. Now the enqueue function. It takes the queue and a value v, and it adds v to the rear. This is the overflow guard, and it comes first. If CQ full is true, there is no room, so we return 0 right away. Nothing else changes. Then we store the value. We write v into Q arrow data at index Q arrow rear, the free slot rear points at. Only after writing do we advance the rear. We set Q arrow rear to rear plus 1, mod capacity. The mod makes the index wrap to the front of the array at the end. Now we raise the count by 1, and we return 1 to report success. The queue holds one more element. The dequeue function does the opposite. It removes a value from the front and writes it into out. Again, the guard comes first. This is the underflow guard. If CQ empty is true, there is nothing to remove, so we return 0 and leave the queue alone. Now we read the front element. The value at out becomes Q arrow data at index Q arrow front. Then we advance the front the same wrapping way, front plus 1 mod capacity. We lower the count by 1 and we return 1. The element is gone. The output shows overflow and underflow both rejected, and all the asserts passing. Because each guard runs before any index moves, a rejected call leaves the queue completely untouched. This is Lab 2. Your goal is to trace a linked queue by hand. After each step, predict the front, the rear, and the contents. Then run the program and check your answers. You have about 20 minutes. Trace this sequence. In Q10, in Q20, in Q30, then dequeue, then in Q40, then dequeue, dequeue, dequeue. Write down the queue after every single step before you run anything. One hint, track front and rear as which node, not which value. After the list empties, both front and rear must read null. It is easy to reset front and forget rear. Let's check the trace together, 1 row per step. Compare each line with what you predicted. Notice front and rear name which node by its value, not just a node. In Q10, the queue has 1 node, so front and rear both name node 10. Contents just 10. In Q20, front still names node 10, but rear now names node 20. contents 1020. Enqueue 30, rear moves to node 30, front is still node 10, contents 102030. First dequeue, it removes 10, the oldest, front now names node 20, rear is still node 30, contents 2030. Enqueue 40, rear moves to node 40, front is still node 20, contents 203040. Deque removes 20, front now names node 30, contents 3040. Another deque removes 30, only one node is left, node 40, so front and rear both name node 40. Now the last deque, the line students most often get wrong. It removes 40, front becomes null, and rear must also become null as a separate step. If you reset front but forget rear, rear dangles at the node you just freed. This is Lab 3, the challenge. Your goal is the sliding window maximum. For every window of size k in an array, report the largest value in that window. The trick is to do it in amortized big O of 1 per step, using a deck of indices. You have about 35 minutes. This is the function to write sliding window max. It takes the array A, its length in, the window size k, and an output array out. The comment shows what out should hold. Out at index I is the maximum of A over the window that starts at index I back the deck with an array of indices. To test it, use the array 1, 3, minus 1, minus 3, 5, 3, 6, 7 with k equal to 3. The answer, the max of each window, is 3, 3, 5, 5, 6, 7. 2 hints here. Store indices, not values, so you can tell when the front index slides out of the window, and keep the deck's values in decreasing order, front to back. Pop the back whenever a smaller candidate could never win. Then the front always holds the current maximum. Let's walk the solution together. Try your own version first, then follow along here. This is the sliding window max function. It fills the output array, one window at a time. First, we make a deck called ix, big enough to hold n indices. Notice we store indices, not values. Now we loop over every index I in the array, from 0 up to n-1. Each pass handles one new element. This check drops indices that fell out of the window on the left. If the front index is less than or equal to I minus k, it is too old for the current window. So we pop it from the front. That keeps every index in the deck inside the current window. This while loop keeps the deck in decreasing order. While the value at the back index is less than or equal to at index I, that back index can never win again, because at index I is at least as large. So we pop those weaker indices from the back, one by one, until the order is decreasing again. Now we push the new index I onto the back. The deck still runs from the largest value at the front to the smallest at the back. Once we have seen at least k elements, the window is full. We record the answer. Out at index I minus k plus 1 becomes at index deque front of ix, and that front always holds the current maximum. When the loop ends, we free the deck, so no memory leaks. The output is 3, 3, 5, 5, 6, 7, exactly as expected. Next, let's trace the deck row by row to see why it is big, O of n. Let's trace the deck. One row per index I. The array is 1, 3, minus 1, minus 3, 5, 3, 6, 7, with window size 3. The deck holds indices, and its values stay decreasing front to back. I is 0, value 1. The deck is empty, so we just push index 0. The deck is index 0. The window is not full yet, so no max. I is 1, value 3. The back index is 0, value 1, which is less than or equal to 3, so we pop it. Then push index 1. The Deque is index 1, still no max. I is 2, value minus 1. Minus 1 does not beat the back, so nothing pops. Push index 2. The window is now full, so we emit A at the front index, index 1, which is 3. I is 3, value minus 3. Again nothing pops. Push index 3. The front is still index 1, so the max is 3. I is 4, value 5. First, the front index 1 has slid out of the window, so it expires. Then 5 beats the back twice, so we pop index 3, then index 2. Push index 4. The Deque is just index 4 and the max is 5. I is 5, value 3. 3 does not beat 5, so nothing pops. Push index 5. The front is index 4, so the max is 5. I is 6, value 6. 6 beats the back twice, so we pop index 5, then index 4. Push index 6. The max is 6. I is 7, value 7. 7 beats index 6, so we pop it. Push index 7. The max is 7. The full output is 3, 3, 5, 5, 6, 7. Each index was pushed once and popped at most once, so the total work is big, O of n, and that is the whole chapter. You built the queue and the Deque from the ground up. Nice work, and I will see you in the next lesson.